Who can tell me what f of 2 is? 1. That's right. How did you know it was 1? That's right. Now, let's imagine this for a second. What if I had whited out just a part of this? Like, oops, sorry, I spilled some white out on the paper. What does it look like f of 2 is going to be? That's right. Before we go any further, this is paramount to this lesson. Raise your hand if you understand why, or if you don't understand why everybody's saying 2 or what it looks like it would be. Well, context clues. If you were to try to connect the dots here, just where does it look like it would be? 2. That's what we're doing today. They're called limits, and it's just using the context clues of your graph to fill in missing points. That's what we're doing. Yeah. Well, we won't be looking at graphs for all of them, but yeah, more or less. Okay. We're going to jump straight back into another graph example. Here's one. Now, answer B first. Who can tell me what the value is at x equals 3? 1. Negative 1. Negative 1. Now, this is how you'll be asked today. They'll say, look at your function. What is the limit as x approaches 3? So you look and you put your I put my finger on it, and as I get closer and closer to 3, what's it going to? Negative 1. Negative. Okay. One thing, you see how this is a nice continuous function? There's no break. So the DOM was different, wasn't it? One of the values was 1, the other was 2, because it was discontinuous. There was a point or a break in the graph somewhere. If there is no break in your graph, and it is continuous, these will always be the same. The point is going to equal the limit. The only time they'll be different is if there's a break of some sort, like the DOM. Let's look at it some more. We'll come back to those. All right. Here's one that's very broken. Now, notice the minus and plus sign after the 2. That means from the left side and from the right side. And I'll show you that right now. Part A. This says, what is the limit of the function as x approaches 2, but only from the left-hand side? So you can use your hand to cover it up. I'm going to use...
I had to go to like 8 different classrooms. They kept sending me around all over the place. I was not going to bring that back to class.
I gave you a new cutoff. That's why they booed you. Hey! I appreciate you. I appreciate you, Brayden. Thank you. And people are going to be wondering what the heck just happened because I'm recording this. Okay. I'll pick these up later because I appreciate it. Hey, I'll tell you what. We will actually use this. If you remind me that the weather's nice, we'll use this one day next week, I promise. In fact, I know the perfect lesson to do it with. So plan for next Wednesday, assuming the weather cooperates. Okay. Back to the lesson. Somebody walked in who we hated, so we booed him. Okay. Just kidding. All right. As x approaches 2 from the left. Now, when you have these today, you can just cover it up with your hand. I am going to cover up. Now, the minus sign means all you need is from the left side of that point. So I'm covering up everything else. So from the left side, as x approaches 2, Brayden, what y value does our function approach as x gets closer to this? What y value does that approach? Yeah, that's all you know. Good job. 4. That's right. So the answer to part A would be 4. That was the limit as x approaches 2 from only the left-hand side. That's what that little minus indicates. So we only look at the left-hand side of 2 and see that it's approaching 4. Now the next one had a plus sign after it. It stands for the right-hand side. So we cover up everything to the right of 2. Well, it's a little harder to do. There we go. Everything to the right of 2. You know what? Just for good measure, I'm going to cover up that 2. Because we're not interested in what happens right at 2, just to the right of it. So, from the right of 2, who can tell me what this function's approaching? What y value? 2. 1, 2. As x approaches 2 from the right, the y value approaches 2. Now, do those two answers, the one from the left and the one from the right, do they go to the same thing? No. One goes to 4, the other goes to 2. If they don't agree, if they're not the same, then the general limit won't exist. Now, if these had both happened to go to the same point, and these were the same, then that's what this would be. This will either be does not exist if they do not match, or it will just be whatever these were if they were the same. What's the difference? In what? Well, it says, as x approaches 2, what is y going to? So as we approach, half of you would say 4, the other half would say 2. There's a disparity. They don't go to the same point. Yeah. That's right. Now what does the actual function equal it to? 4. Yeah, that's the closed dot. What if they had both been open dots? What would it equal? Nothing. It would just not exist if there's no point. We are going to have one like that later on. Questions about that? All right, that is the basis for today's lesson. The only reason some people tend to think it's complicated is because now we're going to do the same thing, but we're not going to look at a graph. So here's an example. Let's say, I'm going to give you a function. Let's say this was some function, okay? And I say, what is the limit as x approaches 2? You are going to have to, on your calculator, and I'll show you how, find the left-hand limit and right-hand limit. If they're the same, that's your answer. If they're not, you write doesn't exist. Now, how do you do that? Well, essentially, as I drug my fingers along here, wasn't I basically looking at f of -1, f of 0, f of 1, and making my way to this? That's what we're going to be doing on the calculator. We're going to take that function, and we're going to plug in values really, really close to the value we're evaluating. So for 2, I would pick numbers just slightly less than 2, like 1.99999, and a number just slightly greater than 2, 2.00001, and I'll plug those into my calculator. And if it gives me the same y value, or very, 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 very similar y values, I know that's my limit. But if I punch in 1 just to the left of 2, and it tells me 4, and I punch in 1 just to the right of 2, and it tells me 2, I'll say it doesn't exist, because they don't go to the same thing. Here's what it looks like without a graph. Now, these, on numbers 1 and 3, they did all the work for you. They already punched in the values. All they want you to see is, do you notice if they're going to the same thing or not? So they said for this one, as x approaches 2, what's our limit? So they punched in numbers less than 2. Now they like you to make an entire xy set and punch in several, 1.9, 1.99, 1.999. You don't have to do that. I say to start out with the ones really close and just compare those numbers. So they punched in all these x values in their calculator and got these y values. Are these going to the same number? What is it? That's your answer. What about this one? They punched in numbers just slightly less than and greater than 0. Are they going to the same number? 3. So that answer would be 3. If these were different, then it would be doesn't exist. Because these numbers are both going towards 3. 2.9996, 2.9996. I'll show you in just a second. Before I leave this screen, another kind of rule of thumb for this section. Remember how I said if it's continuous, it can be the same thing as what the function equals? Yes, I did. Okay. Wow, 3 of 16 heads already down. None of them go. Okay. Who can tell me what makes the function impossible on the side? What have we done that says you can't do that? You divide by, and you have a negative under. That's right. Well, the only ones we're even going to deal with today are these. Zeros under radicals. When you have a 0 under a radical, you have to do this. You have to punch in points on either side of your value to see what it's going to. But if you don't have a 0 in the denominator, then your function's continuous. So all you have to do is plug in that value. Because it's going to be like that second picture we looked at, where they were the same. Because, let me go back to it. If there's no 0 in the denominator, it's going to look like this. And it's not going to be discontinuous. So the value will equal the limit. So on that last one, yes, you could have looked at the chart and gotten 8, but you could have also noticed, hey, 2x squared is continuous. So just plug 2 in for x and see what it equals. 8. Let's look at the next ones. Number 5, is it continuous? So plug in x. 5 times 2 squared. And what would it be? 20. Yeah, that's it. By the way, the paper thing was their idea. I didn't want to do it. Okay, now, number 7. What do you think? Continuous or not? Yeah, but you're right. Some people look at this and they say, ooh, 2 is going to make that impossible. That's true, but are we looking at 2? No, so it's irrelevant. So yeah, essentially, your first step to all of these today is just punch in the number. If it equals something, 0, 1, 2, 3, 4, anything other than something over 0, that's your answer. So 1 over 3 minus 2 is just 1. And that's the answer to 7. I just told you. Punch in the number for x that it gives you in the limit. Unless you get a 0 in the denominator, it's continuous. Then, I'll show you. Actually, that comes down to number 11. I'll show you.
Why would you say like that first one you like to do it?
Well, some people, what's going to give you a 0 in the denominator? An x in the denominator, right? So they look at this and say, ooh, that's we discontinuous of 2. And they're correct. But we're not evaluating 2, so it's not really relevant. Had this been x goes to 2, this wouldn't be 1 anymore. We'd have to do some other math for it, which I'll show you how to do in a second. So, does that make sense? No. I'll tell you. Let's look at this. Number 9. Plug in 0. Tell me what you get. Is that, yeah, 0 over 1 is just 0. We didn't get a 0 in the denominator, so we're happy folks. That's just the answer. What happens if you plug it into number 11? Nope, you get 0 over 0. Anything with a 0 in the bottom is impossible. That means, no. This means it is, there's a break. It's, I'm on this, totally drawing a blank. I've been using the word 50 times already. Yeah, what is the word I've been using for that? Continuous. If you get a 0 in the denominator, it means it's not continuous at that point, and that's when you have to do this stuff. But I'm going to show you, they say construct a table. They want you to punch in all these values, but I'm saying, let's just cut to the chase and look at the ones that matter. What is a number just ever so slightly less than negative 2? Negative what? That's actually slightly greater, but that we can start there. That's all right. So, no, that's fine. So we're going to punch it in. That's bullying, guys. At least he tried. I didn't tell them to do that. All right. A rule of thumb today, always just go to Zoom Standard first. Zoom 6, and that'll put it on the standard window. Okay. Now, if you... The function, just the function, x cubed plus 8 over x plus 2. Now, if you really want to, even though you should have already done it, you can punch in negative 2 for 0. For x. Sure enough, notice, no y value, because it's impossible. So you need to punch in values closer and closer to negative 2. So like you said, let's start on the right-hand side this time. Trace. You said a negative 1.99. Let's get even closer and throw a few more 9s on there. Grab my point. That is a number ridiculously close to negative 2 on the right-hand side. Enter. What y value is that approaching? 12. So we are hoping that when we plug in a number on the other side of 2, negative 2, it will also approach 12. So what's number slightly less than negative 2? Very good. Enter. Is that going to 12? Then that's your limit. If they're the same, that's your limit. Trace. Hit the trace button and then punch it in. Now another kind of rule of thumb that'll help you today, look at the function. Does it look like it has any breaks in it? Then your limit's probably going to exist. It's probably just that one spot that got left over. Now this one, if you're a good factor, I believe this one factors a little bit. But if you get some, you don't have to factor at all today, but if you like algebra, that can save you some time. Like you take this problem, for example. How does the top factor? Let's say this is limit as x approaches negative 2, which would give me 0 over 0. How does that top factor? X, that's right. What cancels? Now if I plug in negative 2, what's it give me? And there's your limit. So you can use algebraic factoring to find your limits today too. But 11.1. 11.1. We're jumping to the last chapter. We're going to take a quick second. I'm going to tell you what our plan is for the rest of the semester. We're going to go ahead and finish up the stuff that I really wanted to hit in the book in this chapter. For the rest of the year, starting the week after next, we're going to... What? Wrong. There are a lot of sections we skipped, and I'm going to go and do about a section a day, and we're just going to lightly touch on it so that you've seen it. I view it as the less important stuff, but I'll introduce it to you. We'll do a few problems, 4 or 5 from that section, but then I'm also going to be giving you some review every day. We're going to review for pretty much 3 weeks, so that by the time the final comes around, you'll have seen everything again. So, because it is cumulative. But anyway, that's why it's chapter 11. All right, same thing here. You plug in 0 for 13, you get 0 plus 0 over 0, which is impossible. So you have to go to your calculator. You can use all your notes. So yes. Yes. How do you think so? I don't remember. Oh, no, it was 12. Remember we punched in those values and the y values went to 12, so it was 12. Negative 2.001 is what you plugged in to get 12. Alright, so where were we? Oh yeah, calculator. Alright, so you graph it. Zoom 6. Yikes. Well, there's a lot of asymptotes, but we're only interested in 0, and we can see that. So, we need to trace. What's a number just less than 0? Negative 0.9999 is close to negative 1. We need negative 0.0000001. Enter. What's it look like the y value is? Yeah, it's going closer to 1. Let's try from the other side. What's the number just greater than 0? 0.0000001. Well, whatever. Enter. And what's it getting closer to? So were they the same? Yes. So what's our limit? 1. Less than 0. If that's what your limit is. Our last one was 2. That's why we did 2. See, that we only chose 0 because that's what it's going to. 15. Same way. Try 15 on your own right now. We'll see if you get it right. You're going to need a calculator. You cannot do all of today's lesson without a calculator. Oops. Oh, make sure you're in radian mode. If you're not in radian mode, it won't show up. Now trace the values around here. Now, I wonder what the natural step size to your calculator is. What I mean by that is, I wonder if you don't even have to punch in those values. Let's see. Hopefully, when you punched it in, you got 0 over 0 and realized that was a problem, or something over 0. It doesn't even matter what it is. So you went to y equals and punched in tangent. What? Oh, sorry. Right. Tangent of x over x graph. There it is. Now, I'm wondering, so first off, you traced 0 and got nothing. I wonder if you just hit the button, how far it would go. Not very far, but still a little too far. So, what's the number just less than 0? And it looks like it's, wow, it's so close it's just going to tell us. It's pretty much 1. Let's try a number greater than 0. And it is also 1. So our limit is 1. Very good. Questions? No? Piecewise are the exact same thing. Piecewise. The beautiful thing about a piecewise is it's basically less than 0 is like that thing we looked at a second ago, like saying from the left-hand side. So this is basically like a left-hand limit and a right-hand limit, that little minus sign and plus sign, and we just need to see if they agree. Are either of these discontinuous functions? So just plug it in. What's this one going to equal when you plug in the limit value? What about this one? Are they the same? That's right. If those don't agree, then it doesn't exist. Yeah. Piecewise, people look at piecewise like they're horrible. They're actually easier because you don't have to punch anything complicated in. It's telling you all the way up to 0 on one side and all the way up on the other side, there's the function. So they're actually easier. Questions about how we got anything on that screen? Okay. Well, we've already done that. Here, you can either plug it in or you can just look at the graph. Who can tell me what 23 is going to be? Yes. How'd you get it? Yeah, just plug 2 in. 1 minus 4. Thanks. Or you could look at the graph. At 2, my y value is -3. Either way will work. What about over here? Yes, that's -5. Okay, let me get back over to this. This is like a half-second problem. There you go, -1. Sine of -5/2 is -1. Of course, you could always calculate it again. -5/2, -1. Just limit. Find the limit of. That's what all these are called. Alrighty. Okay, we've already done that one. Ooh, fun stuff. I'm going to go around and ask every single person in here a question, so ye be ready. All right. Michelle, start with you. Actually, no. Just Mary stepped out. I won't forget her. I'll start the next one. Hailstorm. A, what is, from this picture, what is the limit as x approaches -3 from the left? -3 from the left-hand side. Very good. Very good. From the left-hand side, +2. Adam, right-hand side. -3 from the right-hand side. So you come in on closer to -3 and it stops where? Very good. Before we go any further, it's important that we understand where this is coming from. Raise your hand if you'd like me to explain that a little more. Okay. The little minus and plus sign stands for from the left of that value and from the right of that value. Remember when I put that white box on my screen? All you need is from the right-hand side of -3, which is 2. Sorry, left. This one, from the right-hand side of -3. Cover up everything else. Go into -3, and it is 2. Were they the same? Then your overall limit will be the same thing. It will be whatever these two were, unless they were different, in which case it will not exist. Yes? Yeah, where the graph is, yeah. Even if it was open, you're just looking at where it goes. Yeah. So, C, I just said C. C would be 2 as well. Joseph, what would D be? Yeah, 2. It's continuous. So those should all be the same. If it's continuous, they'll all be the same. Tyler, first, E. -1 from the left. Yes, it would be 4. Oh, I'm sorry, negative 1. From the left? Yes, it would. Emily. F. That's right. It's 3. Dylan, did you get G? Close. What was this one? Tyler, what was this one? No, we did. 4 and 3. If they're not the same, it doesn't exist. If they are the same, it's just that. Emily, what's H going to be? Is there a dot anywhere? Nope, so it doesn't exist. Yeah. Does not exist. D and E. That's what I would write. Boog. I. It would be. Brayden. J. Very good. Josh. K. That's right. They're the same. It's just going to be that. Dylan. L. Very good. Very good. Because the actual point is down here. Now, just remember, the point itself has absolutely no bearing on the limit. It's just kind of interesting thing to see when they're different. But the point itself does not change the limit at all. Right here? Let's see. Positive 3 from the left-hand side. So you would come into positive 3 from the left, and you would stop at 2. Okay? Darn, ran out of problems. I know you guys feel bad. Oh, wait, I have one. Okay. There it is. I'm going to let you take the first hard one. 2 from the left. These are tricky because it jumps so much. Hey, 31 maybe?
Are you looking at X or Y?
We're looking, for your answer, Y value. You're looking at these X's, but the Y's that they correspond with is your answer. Any ideas? Let's see. As X approaches 2 from the left-hand side, it would be 1. Very good. Brittany, what about B? Close. This one's tricky. As it approaches 2 from the right-hand side, that would be 2. So therefore, what would my overall limit be, Michelle? Yep. It would be not exist because these weren't the same. These have to be the same in order for this one to exist. Oh, okay. Okay, what would D be? Where's the actual point that X equals 2? It is. At f of 2, where's our Y value? 2. Caitlin, what would E be? .5 is here, right? So where, that's here. From the left-hand side, what's that approaching? 2. And from the right-hand side, what's it approaching, Crystal? 2. This one looks weird because there's so many discontinuities. We think it's going to be a breakpoint, but believe it or not, at 2.5, this is a continuous function. There's no break at that point. So these are going to be the same all the way across the board. 2, 2, 2, 2, 2. Questions about anything that's on the screen right now? That's probably as bad as it gets. Alrighty. The last slide is nothing more than a combination of everything we've done. It's just a whole bunch of examples. Number, I'll say right now, number 33, 35, 37, 43, and 45, just plug in. Plug in. You might have e's. You'll have a natural log in there. Just plug them in. 39, oh, you can plug that one in too, because we're not even looking at zeros. plug it in. This is the only one you might have to do in the calculator. Take values on either side of +1. The only other thing I want to look at before I cut you loose, what does this mean? Don't look at this, we'll cut off with the prop above it, but look at 47. Who can tell me what I need to do there? Well, what that even mean? It is a line, but what do you say? So, top one, bottom one. Top one, you're right. This is saying that you have a function. Everywhere but 2, you have a function. But at that one random point, it's down here. But remember how we said the point doesn't matter with limits at all? Any problem you have today where it gives you x equals and a piecewise, you don't need it at all. So I could cover that up. It's completely worthless. So I'm just curious then, as x approaches 2, plug it into your function, what is it? 3. Your limit would be 3. Good. All right. That's about it. Well, no. 49 doesn't say x equals. This is a two-sided limit. You have to plug it into both. What is it on the top one? What is it on the bottom? So what's the overall? Exactly. You got it. Okay. There you go. Yes, sir.